Right, thank you. So I want to talk about some work that I've been doing where we wanted to take player movement in football games and make some predictions about the near future. And so from a research perspective, this came down to a basic problem: is it possible to design some sort of machine learning framework that can learn directly from raw tracking data? Now, there's a few things to unpack in this statement over the next few slides. So just in terms of raw input data, we're essentially talking about tracking data. We want to be able to track each of the players on the pitch as they move about multiple times per second. So essentially, this tracking data samples each player as they're moving, and if you string those together, you get a description of a curve that the player follows. And we want to take this data, and along with some additional data, essentially event log data, describes what's going on. So in a football game, the pass, the tackle, and these events get logged, and they have a time associated with them that tells you when that exactly happened, and possibly also a location. And the third piece of data we have is just some metadata around the game. So for their height, their position, and for the game, it's the playing surface, the weather, and we also have the game state, so the scores, the clock, etc. And so we want to take this data, we want to take this data and we want to learn something about the near future from it. And so I'll just describe a couple of examples that I'll come back to throughout this talk. In this first one, we have some player trajectories, and for each player we can see a small dot and then a curve connecting them to the larger dot with their position. And each of these trajectories, the small dot is at the snap, and the larger dot is at the moment where the quarterback who has the ball is just about to make a pass. And so at that time, when the quarterback's about to make a pass, we want to make some predictions about each of the eligible receivers. And essentially we want to predict, if the quarterback were to pass to each of the receivers, where that pass would land. So we can see for each of the receivers there's a dotted line connected to a point, and that's where we would predict the pass would land in a second or two after the quarterback throws it. We also want to predict for each of those passes what the percentage, what the probability that the pass will be completed. So essentially, what the percentage that the receiver will catch a pass. And then we just want to predict also the air yards gained on that pass. In a second example, again, we've got the trajectories of all the players, and this time we have a wide receiver in the centre of the picture. He has the ball, and we can see that he's moving towards the sideline at the bottom of the screen, and we'd like to make some predictions about where he is most likely to be tackled. So here, the model's predicting this red dot towards the bottom of the screen, and that's where the tackle is most likely to occur. And then for each of the defensive players who are in silver, for each player, if they're the one who's going to make the tackle, we want to assign a probability to that. So clearly the player, the inside linebacker just next to the wide receiver at that moment is the player who's most likely to make the tackle. So these are prediction problems. They're quite a well-studied class of problem, and machine learning is generally been shown across a wide variety of fields to be effective at these sort of problems. So that's the sort of approach we looked at, and when we did that, we soon came across a problem that I think anybody who's worked with tracking data would be familiar with. You essentially have this mismatch between what the structure that machine learning algorithms assume their data looks like as an input and what tracking data actually looks like. And that sort of, and I'm simplifying this quite drastically here, but essentially machine learning algorithms work best where you have a very structured input. So it might just be a vector of numbers, and in each component in that vector describes some particular phenomena. So you might have two examples, and the first component might be the velocity of a quarterback, and that's consistent from the one example to the next. The next component might be the distance from the nearest defender to the quarterback. But the problem is you have, with tracking data, you have something closer to this, where you have essentially a multi-dimensional tensor of data, and because each play, in this case in football, the time between, say, the snap and the pass varies from one example to another, you have this issue where the duration of the play differs, and that manifests itself in the length of the trajectories is different. And so this we can see in the third dimension, and these tensors varies from one example to the other. And a second more profound problem, particularly with football, is that on each play the personnel will change. So in one play you may have 3 wide receivers, and in another one you might have 2. And because that means you can't line up your data so it's consistent between examples. So in this toy example I have here, each column is a different player, and we've color-coded columns denoting the player positions. And so you can see there's no way we can order the players and the trajectories for players in these 2 examples so that they're consistent from one example to the next. So these are, we call these, the first one a variable duration problem, and the second one is this player ordering problem. And so these are the key problems we were trying to solve with the model that we wanted to build. And so traditionally, a way that's been used that's quite effective at dealing with this problem is to have a feature engineering phase in your model. And essentially what this does is you speak to an expert and you decide what are the important features of a play for a particular problem you're trying to solve. So if we're trying to predict how likely a pass is to succeed, we might decide that the distance from the receiver to the nearest defender is an important feature. And so you'll decide on a set of these features. You'll then have to code up routines to populate them. But essentially what you're doing is you're taking our trajectory data and you're deciding a function that will convert it into a nice, well-organized vector for each play. So this obviously has a few drawbacks. It takes time. You've got to rely on some domain expertise to decide what are the important features. You've then got to code up the routines to populate them. And you can never practically define enough features to capture the entire context of what's going on. You've got 22 players who've probably been moving in the play for a couple of seconds. There's been all sorts of interactions, adjustments in their movements. And so it's a very rich data set of information, and you're just going to lose some of that when you design these features. So what we wanted to do is try and avoid this step, and essentially we wanted to build a deep neural network that would learn this feature representation automatically as an intermediate step in the model. So the data through the machine learning algorithm would inform which features are important, and it would decide which ones to include in this intermediate representation. So that's the basic motivation for why we wanted to do this. And so we came up with this framework to address this issue. And so we settled on this framework, which I'll describe in the next few slides. But just circling back to these two fundamental issues I talked about, in terms of a variable duration problem, we are using essentially a 1D convolution. So it's a machine learning component, an activation that is used to describe what's happening along each trajectory. And for the player ordering problem, we use a set-based model architecture. So this essentially treats all of the players in the input as just a set and doesn't make any assumptions about the ordering, doesn't make any assumptions about the number of players that are included. It just works regardless of the order that the input comes in at. And so we can use this framework without modification for all of the particular prediction problems I was talking about earlier. So just as a high-level overview of this framework, it's a multi-layer framework. The data essentially flows from left to right, and each layer performs a particular task. So in the initial layers, we want to take our input trajectories that all have a variable duration, and we use 1D convolutions that basically slide along them and detect important movements that are occurring in each trajectory individually. So this might be things like players turning, players accelerating. We can detect those along the length of each trajectory. And we use adaptive pooling layers to standardize the length of the output trajectories. So these essentially find the most important feature from the detections at each fractional interval along the trajectories. So if we have two trajectories that are of different lengths, it will just look at what's the most important thing that happens in the first 10%, the second 10%, the third 10%, etc. So that gives us standardization from varying length trajectories. The next step is, and this is all set-based, is we include some player details just about their position, their height, their weights, and in this layer we want to look at interactions between players. So we want the model to be able to detect when two players, by their movements, are performing some higher level action. So for example, if a defender and an attacker, they move into close proximity with each other, that indicates that a block has occurred. And so this layer in the model will detect these sort of interactions. And then the third layer, it takes these temporal sequences of interactions between players, and it wants to learn essentially just a single representation of the entire scene. So it wants to learn some description of the entire play. So it includes, we include some context around the play, so the down count, the yards, etc. And we want to learn just a single representation, a single vector that describes a play. And so back to the feature representation, this is essentially trying to do the same thing, but it's all done just learning directly from the data without any input or guidance about what are the important features these features are learnt directly. And then the final layer is just for each particular prediction problem, we just need to build a small network that takes that representation of each play and makes the actual prediction. So for example, if we want to predict the pass completion percentage, we'll build a small network to do that. For the location of a tackler, we build a small network to do that. The rest of the model is the same regardless of the prediction problem we're working on. So we took this model and we implemented it on these two examples. We constructed models for the two examples I discussed earlier for pass prediction and tackle prediction. And we trained this using the data from the data set from the NFL Big Data Bowl from last year. So that's it's essentially the NGS tracking data from the first 6 weeks of the 2017 season. And so just some high-level raw performance metrics on this. We trained the model and we were able to achieve some relatively good performance given the small data set that showed that the model seemed to be learning and seemed to be able to make informed decisions just purely based on this data. But what's possibly more informative is if we just look at some individual examples where we run the play out and we look at the predictions that are made, and we can just discuss some of what's going on. So in this case, the quarterback has got his eligible receivers, and in each case, there's a prediction of where the pass is going to land and a percentage of what the probability that that pass is going to be completed. And it's fairly clear that the further passes are down the field, the less likely they are to be completed, which is, I think, fairly intuitive. Passes that are longer are more risky. They have a higher payoff, but that's fairly understandable. But if we look at this next example of another passing play, and if we look at the wide receiver in the middle of the field, and we notice that his completion percentage, 56.8%, is a lot lower than the other options that are actually longer passes. But if you notice that as it scrolls around, he's actually being covered by two defenders. So it seems as though the model is taking into account the fact that the more coverage that the receiver is under, the more difficult it is for a pass to be completed, and the model adjusts its prediction on the pass completion accordingly. So this next example is a tackle situation where the wide receiver here has received the ball, and we notice that the strong safety who's just behind him is the one who's most likely to make the tackle. But as the play rolls out from the point where it freezes, we notice that the receiver gets around that strong safety and starts heading upfield. And at that point, the percentage associated with that player drops off particularly quickly, and it's this free safety who's coming from deeper, who then starts accumulating being the most likely tackler in this situation. And just a second tackle example, here we've got a running back who's running towards the sideline at the top of the screen, but we notice that the most likely tackle location is already down on the other, towards the bottom of the screen from where that player is. And it seems as though we can see when the animation scrolls back around that this running back, he's running into traffic, And so he makes a decision at some point to turn around and head back towards the more open area of the field. And it seems like the model is already starting to predict that that's a likely occurrence, and it's adjusting its prediction of where the tackle is likely to occur based on that. And so it seems like in all these cases, the model's starting to pick up concepts that are intuitive and help to describe what is actually going on in this complex scene with 22 players moving around, and is able to discern what's important and what isn't. So that's what I wanted to speak to you about today. Just to recap, we've designed a framework that's learning directly from raw tracking data without the need for any pre-processing or feature engineering beforehand. And we were able to implement this on a number of prediction problems, and it seems to work pretty well for those. The results are quite encouraging. It works well on quite a small, modest-sized data set, and would definitely be interested to see how it works in more training data, and also look at it at other scenarios, other sports. And so thank you for your time, and I'm happy to answer any questions.
All right, we have a mic that we give around.
Hi, thank you. That was really interesting. So my question is, it sort of seemed like in the earlier... sorry.
Can you lift the microphone?
Oh.
Yeah.
So it sort of seemed like in the earlier slides that you said you used the trajectories as part of the deep learning net.
Yeah.
But when you were showing the visuals, it just seemed like you were just using snapshots of that exact moment. So when you're making the predictions, are you using the trajectory up until the point of that moment, or are you just using the snapshot?
Yeah, absolutely. So the model makes a prediction in these examples, so from the snap until either when the pass is made or in the running situation when the ball carrier is heading upfield. It takes into account all the movements that have occurred before that. And so, yeah, definitely. Cool. But we are making a prediction at a particular point in time, so we take everything we know up until that point and then predict a future event just based on that historical information.
Cool, thank you.
No problem.
How did you assess model accuracy after you fit your net to have confidence that what you fit was, what you're looking for?
So we just used usual sort of holdout. So we trained the model on 80% of the data and held out 20% to use for evaluation. And then, so for each of the tasks, the prediction tasks, we know what happens in the future because we've got the data. So we know where the tackle actually occurs in each example, and we can use that to evaluate how far our prediction is away from the actual result.
How many other model architectures did you consider, and sort of where are you thinking about extending this work further with other changes to the architecture?
Yeah, so in terms of the variable duration of the trajectories, the obvious other way to handle that is to use some sort of recurrent model where, so like an LTSM or something that is sequentially models the way the play unfolds. But this is probably purely down to just the size of the data set, but we had trouble learning using that model, whereas with the more simple convolutions, it trained better, we were getting better results. On the set-based side, the other thing that I'm quite interested to look at is using attention-based mechanisms that are quite popular in natural language processing. So like transformers, which have the same property where they treat the input without any implicit ordering. So there are definitely things we could try to improve things.
All right, we have time for one last question.
Yeah, I can think of a lot of kind of obvious applications of this system, whether it's like coaches using this to inform decisions or maybe having like a replay system on TV broadcasts. Did you have a specific application in mind when you designed the system? And if so, how did that kind of affect the way that you designed it?
Yeah, so initially it was just for these prediction problems I described. We had a client who was looking to make these sort of predictions. It seems like this would work well in other sports as well. So one of the examples we've been looking at is in hockey. You have this problem where you have power play situations where the number of players on the ice varies from one possession to another, and so you need to account for that if you want to make some sort of predictions. And this set-based architecture handles that as well. It doesn't make any assumptions about how many trajectories it's seeing. And possibly also, I was just thinking with the previous talk, where you have the broadcast tracking and you're capturing the player trajectories and broadcast tracking, you're going to have problems where players are off the screen, and so you won't see those players won't be recorded for variable duration. So again, you'll have this situation where not all the players are included in the scene, and you'll be able to handle that with this sort of architecture.
All right, please give it up for Michael. Thank you very much. And we'll be back at 1:30.